Hey there, class. Mr. Pusky here. Hope you're having a good day so far. We're continuing with Chapter 8. This is 8.1, Day 2. It's about exponential growth. Excuse me. So the essential questions on this packet is, what is the model for exponential growth? What is the compound interest formula? And how can I use these formulas to solve problems involving exponential growth? So exponential growth is, we talked about exponential functions. It's basically... you have a base amount or a principal amount, what you start with, and you multiply it by a formula. You multiply it by a percentage each time, and it's going to basically increase by a certain percentage every time that you you compound the interest. Okay, so interest is what you earn over time, and depending on compound interest can affect whether how many times you do that in a year, or how many times you do that in every couple of years or something. Okay, so for example, the reason that exponential growth is different than a linear model is that it takes a percentage of like the new percentage, basically. So if you start with $1,000, and then after you compound the interest, or you calculate it every time, then you have like 1,013. Then the new, if you're multiplying by the compound interest, will take this new number, and it will sorry about that. It will calculate the interest based on the new number instead of just the original number. Okay, so simple interest, it'll just calculate interest over time, but compound interest or exponential growth, it will calculate interest that you earn. You earn interest on the new amount that you made as well, not just the original amount, if that makes sense. Okay, so let's get right into this here. So the standard form of an exponential growth model is this. It is y equals a times 1 plus r all to the t power. But also exponential growth also can be used for modeling like population growth and stuff too. It doesn't have to be just banking stuff. So that's kind of what we're talking about here, okay? So y is going to be our current, it's actually, I'm not going to write that. I'm going to write something different here. Y is our ending amount. Okay, y is our ending amount, okay? And a is going to be our initial or starting amount. Okay, so sometimes you're calculating the ending amount, sometimes you're calculating the initial amount, all right? T is going to stand for time in years, or whatever unit of time you're going to use. It could be seconds, it could be minutes, it could be hours. R is going to be our percent of increase, which is, you need to write it as a decimal. I got to be careful with that. Write it as a decimal. And then 1 plus r is going to be what's called our growth factor. Oops, growth factor. Okay? So let's get right into this here. So we have example 1 says the cost of tuition C can be modeled by C equals 4,300 times 1 plus, or 1.04 all to the t power, where t is the time since, it's the year since 1990. Okay? So, what is 1.04? Well, whatever's in parentheses up here, if you look at it, that's going to be our growth factor. So, 1 plus r, which is our growth factor, is going to equal 1.04. Okay? Whatever's in the parentheses, you set that equal to 1 plus r. All right? Okay, what's our initial amount? What are we starting with? Well, our initial amount, if you look at the original problem here, is a, and a in this case is going to be 4,300. All right? Our growth factor is whatever in parentheses, which is 1 plus r. In that case, is going to be 1.04. And then the percent of increase is a little bit trickier to calculate. It's going to be how far from 1 the growth factor is. So the way I would probably do this, if you're worried about calculating it, you can see how far from 1. You can see it's 0.04 above 1, so it's going to be 0.04, which is 4%. But you can solve it this way. Here, I'll do this over here. Just solve for r by subtracting 1 from both sides. We get r equals 1.04 minus 1 is 0.04. And then to convert that to a percent, you move the decimal 2 to the right. It's going to be 4%. Okay? So our percent of increase is going to be 0.04, which equals 4%. So 4% is our final answer for that one. Okay? But yeah, the percent of increase or percent of decrease, if we're talking about exponential decay, is going to be how far from 1 it is. All right, sounds good. Example 2. In 1980, about 2,180,000 U.S. workers worked at home. During the next 10 years, the number of workers working at home increased 5% per year. Write a model giving the numbers in millions of workers working at home T years after 1980. Okay. So we need to calculate what we know here. So what's 2,180,000? Well, that's going to be our A. That's going to be our starting amount. All right. Next 10 years. That's going to be our T is 10 years. And looks like our R is 5%. Well, what's 5% as a decimal? We got to go the opposite direction now. So if it's given as a percent, you go the opposite direction. If it's given as R, you're going to go to the right. So we're going to move the decimal 2 to the left, which is going to be 0.05. It's going to be our R. Okay? All right, sounds good. So we are going to plug in. So we have Y equals, it's A times 1 plus R, all to the T. So in this case, it's going to be Y equals A is 2,180,000 times 1 plus R, in this case, is 0.05. So like I said, if you're calculating the percent, if you're given the percent, you need to move the decimal 2 to the left. If you're looking for the percent, picked a bad time to start recording. If you're looking for the percent, you need to move the decimal 2 to the right. Okay, so if it's being plugged into here, it's going to be as a decimal. Okay, so we're going to do our time, which is 10 in this case. All right, so actually, I'm going to erase, I wrote 10 here. I'm going to put to the T power here. So what we're actually going to do is, it says we're going to graph the model. I'm not going to graph the model because when you do that, it's going to be looks like it's pretty much a straight line. It's not going to really demonstrate exponential growth too well. But what we're going to do is we're going to check 0, 1, 2. We're just going to check 3 years with this model. And it will kind of, just so you get the practice with it. So I would get in the habit of plugging this into your calculator. And for every T, so this is T equals 0. This is T equals 1. This is T equals 2. Just get in the habit of trying to plug that into your calculator. Make sure you know how to do that. And you should get these numbers. You should get 2.18 million for this one. You should get 2.289 million for 1 year. 2.4 million for this, and 2.52 million for this. And I'll write out the actual numbers here in a second. So I can zoom in here. Okay, so those are the numbers. If you plug those into your calculator, these are the numbers that you should get. If you're not getting those numbers, make sure you talk to me in person and we can figure out why you're getting weird numbers. But yeah, that's how you plug it in. So we're actually not going to graph it because if you do graph it, these numbers are going to basically make a straight line, which is not going to demonstrate exponential growth too well, okay? All right, let's move on to compound interest now. All right, so like I was talking about before, compound interest is interest paid on the initial amount called the principal and the previously earned interest. So you're basically paying interest on the initial amount and also the previously earned interest. So you're actually paying interest on more than just the original amount, which makes it more, if you're working on in a bank at least, like a banking establishment or organization, a good interest rate and using compound interest will be a good thing. But so here's the formula, compound interest formula. We have A equals P times 1 plus R over N, all to the NT. Okay, so let's fill in what we know about what this means. So A is our balance. P is our principal, and what principal means, it's your initial investment. R is our annual rate. And you want to write it as a decimal. What happens, actually one of the most common ways to mess up these kind of formulas, everybody that's watching this, is that if you don't convert it to a decimal, so for example, if you have, it's a 2% interest rate, and you put 2, if you use the number 2, that actually equals 200%, okay? So if you're doing 2%, you actually need to move the decimal 2 to the left, which is 0.02, because 2 is actually 200%. Okay, 2 is actually 200%, which means you got to be careful. Okay, that's the biggest way you can mess up these problems and get really weird, crazy big or crazy small numbers, is that you use the wrong number. Okay, all right. T is time in years, and then N is the number of times it's compounded per year. So the number of times that you take what you earned and applying interest to it. And so they'll say like it's compounded annually, semi-annually, or quarterly. Annually is N equals 1 time. Semi-annually is N equals 2 times. And quarterly is N equals 4 times. All right, sounds good. Let's get into this now. So we have I am fine, or EM fine, whatever that is there. It deposits $1,500 in an account that pays 6% annual interest compounded annually. Find the balance after 5 years. Okay, so we're going to plug into the formula. Y equals P times 1 plus R over N, all to the NT. So we need to figure out all these different things here. So what do we start with? What's our starting investment? Well, our P is going to be $1,500. That's what we paid. That's what we started to be invested. Okay. What's our R? It's 6%. Well, what's 6% is a decimal? We got to convert it to a decimal. It's 0.06. Good. Compounded annually means we're going to have N equals 1. That's the number of times it's compounded. And our time is 5 years. This is going to be our time. Okay, so let's plug it in now. So we have Y equals, our P is 1,500. Times 1 plus, and then it's R over N, so R is 0.06, all over 1, all to the 1 times the number of time, which is 5 years. So it's going to be Y equals 1,500 times 1 plus 0.06, all to the 5th power. So Y is going to be approximately, if you plug that into your calculator, you should get approximately 2007.34, or $2,007.34. And there we go. All right, why don't you see if you can try example 2 on your own, and then we'll go through it in a second. All right, I actually just realized that number 2 is a little bit trickier because they don't give you, they give you a time that's 2 years and 3 months. We actually have to convert that all to years, basically, okay? So it's actually a little bit tricky, so I apologize if you tried that and got a little confused, but let's go through this here. So we have 2 years and 3 months. Okay, well, 2 years is how many months? Well, each year is 12 months. We have 2 of those, which is 24, and then we have 3 months on top of that, so we're going to have 27 months. We're going to use dimensional analysis or unit conversion. And then we're going to convert that to years. So we're going to go, how many months are in a year? Well, we got 12 months in 1 year. So then these are going to cancel. Multiply straight across, you're going to get 27 over 12, which is going to be equal to, when you simplify that, 2.25. Because we need our answer to be in years if we're going to do this problem, okay? So it's 2.25 years. All right, sounds good. That's our T. Our T is 2.5 years. Okay, let's go ahead and read this now. So G honestly deposited $3,230 in an account that pays 4.5% annual interest compounded semi-annually. Find the balance after 2 years and 3 months. We already figured out what years it's going to be. It's 2.25. All right, what's our P? What's our initial amount? It's going to be 3,230. Our R is going to be 4.5. Convert that to a decimal, 12.045. And compounded semi-annually is n equals 2. So we're going to plug into the formula. So we have y equals, it's P times 1 plus R over N, also the NT. So y equals, P is 3,230. So 1 plus 0.045 is our R, all over N, which is 2, all to the 2, which is N, times T, which is 2.25. So if we simplify this, we're going to get y equals 3230 times 1. It's going to be 1.0225, all to the 4.5. By simplifying this and simplifying that. And if you plug that into your calculator, you're going to get y is approximately, it's going to be $3,570.16. All right, and that is compound interest formula and exponential growth formula. So hopefully that makes good sense. It's really just plugging into formulas and figuring out what each part represents, and just be careful that everything, like our units, are in years. And that was the tricky part right over here with this one. But otherwise, thank you for watching. Have a great day. We will talk soon.